Okay, before continuing, we're going to take a look at our picture of a neuron. And I've shaded the soma and the dendrites with these green lines so you guys can know that in this area is where the PSBs is created. And in this box here, you can see that iPSBs plus ePSBs will give us the postsynaptic potential PSP, or otherwise known as the combined postsynaptic potential. And if it is past threshold, the postsynaptic potential, you'll get an action potential. If not past threshold, you get nothing. So where is this postsynaptic potential felt, where if past threshold, you'll get an action potential? And that is in this area right here, the AIS. Now, the AIS is part of the axon. Okay, so let me get rid of this box. So the axon contains the axon initial segment. I mean, it is called the axon initial segment, right? So all throughout the axon, you have the voltage-gated sodium channels and the voltage-gated potassium channels that we talked about. And those are the ones that have the closed, open, and inactive state, and then back to closed. Okay? Those are the ones that we've gotten to know in the beginning of section 2.2. Now, what makes the axon initial segment special? It still has these two channels, but what else does it have? And how does it compute the strength of action potentials that are going to travel down the axon toward the axon terminal ends and eventually lead to the presynaptic membrane on those ends becoming depolarized and activating voltage-gated calcium channels and leading to neurotransmitter release. But before we continue, it is really important to know that an action potential starts here. It doesn't start at the soma and the dendrites. There is no action potential in the soma and the dendrites. Before continuing, there is a concept that we're just going to go over because it'll make what we're going to discuss later a lot easier. If I have an axon membrane, and this is my axon membrane, okay? And of course here we have voltage. So we're doing our action potential in the manner where we're not looking at time. Our x-axis is going to be the axon membrane or distance. And of course this will be in millivolts here, the membrane potential. And we're going to have some max here so I can keep track of it. And we have an action potential that's fired, and it looks like this, right? And it travels in this direction. Now we're going to look at it in the classical way of the x-axis being time. Milliseconds. And membrane potential in millivolts. Again, we have some sort of max. This would be about plus 50. And this would be about minus 70. And we can go a little bit lower, and we have minus 90 right here, right? And our action potential will look like this, where you have a depolarization phase starting, repolarization phase, hyperpolarization phase, and then back to resting potential. Now, if the membrane, the axonic membrane, is made a little bit more permeable to potassium than it usually is, we have the potassium leak channels, so it is already slightly permeable to potassium, but if it is made more permeable to potassium, then it makes it a little bit more difficult to initiate an action potential. Now, why is that the case? Well, let's look at the concentrations, right? And remembering this is extra, and this is cytosol. And for potassium, we have about 5 to 10 millimolarities outside, and we have about 140 millimolarities inside. And we know that it's negative inside the cell when you're at resting potential, positive out. We're at minus 70 millivolts. And we know that potassium's electrochemical gradient is pointing slightly out. And we know sodium 145 millimolarity. Outside, about 5 millimolarity in. And we know that this is pointing directly in very strongly because both the chemical gradient and the voltage gradient, or the potential gradient, is pointing in. So let's make the membrane permeable to sodium. If we make the membrane permeable to sodium, what will happen is sodium will come in and we get our depolarization, right? So let's say that the membrane potential is now moved toward becoming fully depolarized and we're at plus 50. And we're positive in, negative out, and the gradients don't change, so we're not going to even write them because the gradients don't, and this is extra, and this is cytosol. And let's just remember that extracellular is always on the right and cytosol is on the left from this point on. Now, this depolarization, this arrow right here, it's not like the membrane instantaneously goes from minus 70 to plus 50. We have this whole phase of depolarization, right? And what is happening during this phase of depolarization is simply that voltage-gated sodium channels are depolarizing the membrane, and depolarization is the movement of the membrane potential towards a positive, meaning that you're going from minus 70 and you're moving up. You're going towards 0 and you're increasing the potential on the membrane. You're making the inside more positive, so you're moving toward plus 50. This whole movement of going up from minus 70 to plus 50. When you depolarize the membrane, this is a positive feedback loop on the voltage-gated sodium channels themselves, and that leads to this quick rise, this quick spike that happens in a short period of time. It's a very strong positive feedback loop. Anytime you have a positive feedback loop where a system is actually feeding itself immediately, it can be very quick. The system can basically go to maximum very quickly. And that's what we see with this. Now, if you sort of slow down this positive feedback loop a little bit, then it takes a little bit longer to initiate this depolarization phase. Really, the depolarization phase does not begin until this point. This is where that exponential growth is happening, and that's because you have this strong positive feedback loop. So how can you slow this down? Well, you can slow this down by making the membrane more permeable to potassium. If I make the membrane more permeable to potassium, what will happen is, and we'll have this other scenario here, as the membrane is depolarizing slowly, right? We're still kind of negative here. We're kind of positive out, but instead of minus 70, let's say we're at minus 30. Okay? Now, if you're at minus 30, then the inside is less negative, so the electrochemical gradient for potassium is pointing out even more, a little bit more than before. Sodium's electrochemical gradient is still pointing in. So as sodium is coming in, because the membrane is becoming depolarized, so you have plus charge going this way and plus charge coming in. So plus charge is coming in and plus charge is going out, so it takes longer to depolarize the membrane, just because the membrane was made more permeable to potassium. So if I were to look at it, where my y-axis is time, and my x-axis is millivolts and membrane potential, then I have one scenario. The membrane is just regularly permeable to potassium because of the leak channels. There's nothing else going on. Then I might have action potentials looking like this. One comes up at that patch of membrane, another one comes up after it, another one follows. But if I make the membrane more permeable to potassium, then it will look like this. And it depends on how permeable you make it to potassium. What will happen is it'll take longer to depolarize the membrane and get past that threshold to get that initiation and then get the depolarization phase. After that, everything looks normal. and then it takes again longer to initiate the depolarization phase. Then after the depolarization phase is activated, everything else looks the same. I know the peaks are a little bit off. They're not all at the same level. Just imagine that they are, okay? So by making the membrane permeable to potassium, what you're doing is you're increasing the time required to depolarize the membrane enough to get that depolarization phase going. This phase that is highlighted here. Right here. That's all that's happening. And that is because in that initial events of voltage-gated sodium channels opening, since positive charge is coming in and positive charge is leaving, you need more positive charge to come in this direction because of the voltage-gated sodium channels to initiate that depolarization phase. Now, if you keep making the membrane permeable to potassium more and more and more, what will happen is eventually an action potential cannot be generated even if the initial depolarization, the PSP, says it should. Why? Because at that point, as positive charge comes in, positive charge leaves. Because potassium's electrochemical gradient is pointing out and sodium's is pointing in, and they will simply trade positive charges, and you never get past that threshold required to initiate an action potential. So with all that said, now we can get back to the study guide. So this is going to answer the question that we were trying to get at when we ended the last video. And that is, how does a neuron compute the frequency of action potentials to fire down its axon? Why is this important? We talked about why it's important, because if you have a strong signal coming in to the soma and the dendrites, activating signals, those excitatory signals, then you want the action potential to mimic the strength. So you want a higher frequency action potential. Now, if the signals coming in to the soma and the dendrite are not that strong because maybe not many excitatory synapses are activated, or very much activated, and you have some inhibitory synapses activated, then you want the action potential being fired to mimic that weak signal, so a low frequency action potential. This computation at the AIS is done by a type of voltage-gated potassium channel that is only found at the AIS. Right off the bat, we know that this computation, this transfer of signal from a PSP to an action potential, is done at the axon initial segment. And what protein is responsible for it is some types of voltage-gated potassium channels that are only found at the AIS. At the AIS, there exist the voltage-gated sodium and potassium channels we discussed previously, and we talked about that, right? But unique to the AIS is the rapidly inactivating potassium channels. This channel has a higher likelihood of being in the open position if the PSP is low, and lower probability of being open if the PSP is higher. At pass but near threshold, this channel is making the AIS membrane permeable to potassium. For an action potential to form, more sodium has to enter to produce the depolarization phase of an action potential than when the membrane is not permeable to potassium. To this extent, this leads to lowering the action potential frequency. So the main thing to note is that this channel, this rapidly inactivating potassium channel, has a higher likelihood of being open when the PSP is low, and a lower probability of being open if the PSP is higher. So at low PSP, the AIS membrane is permeable to potassium more than it would be if you had a higher PSP. And at lower PSPs, with the AIS membrane being very permeable to potassium, it takes longer to initiate an action potential. So the frequency of action potentials will be lower. Where at higher PSPs, it is less permeable to potassium, and it is easier to initiate an action potential, so you're going to have a higher frequency of action potentials being fired. There are two other channels that are unique to the AIS. A voltage-gated calcium channel and a calcium-activating potassium channel. Now this is very interesting. So again, we see our friend the voltage-gated calcium channel. But now we have this calcium activating potassium channel. What type of channel is this? This is a ligand-gated channel that its ligand binding pockets are in the cytosol, and the ligand for those ligand binding pockets is calcium. Okay? So every time an action potential forms at the AIS, voltage-gated calcium channels open and calcium diffuses into the cytosol, down its electrochemical gradient. If the AIS is forming action potentials at a higher rate, high frequency, the local concentration of calcium will increase. As the calcium concentration increases, calcium binds to the ligand binding pockets of calcium activating potassium channels. This leads to the AIS membrane becoming permeable to potassium, thus decreasing the frequency of action potentials being formed. Therefore, if the PSP is high, i.e., a strong signal, initially action potential frequencies will be high. If the strong signal from the soma persists, the cytosolic concentration of calcium increases at the AIS, and calcium-activated potassium channels go to the open state. This permeability to potassium lowers the frequency of action potential formation, even though the signal from the soma is strong. This is a form of adaptation, where the neuron loses sensitivity to a strong signal it is receiving over time. So what is this? What do we mean by adaptation? The example that the book has, and I think it's a really good example, is that when you first put your clothes on, or you put your backpack on your shoulder, if it's not too heavy, you feel it. But after a while, you stop feeling it. So if you have a persistent signal coming in, what will happen is eventually the neurons will adapt and they will stop sending that signal in a very strong way, which is by forming action potentials. So over time, the frequency of action potentials lowers, even though it was strong in the beginning. So what is happening here? So if we sort of draw it out, and we do have this picture here, and what we're going to do is get rid of the green action potentials, because we made our point with that. You can think that at every peak, what's happening is the voltage-gated calcium channels are opening at the AIS. So this is going to be at the AIS. And you have calcium coming into the cell, into the cytosol at each of these points. And as calcium enters, eventually what will happen is calcium concentrations will keep increasing, and then these calcium-activated potassium channels start to open. So what that will look like is something like this. Now remember, you need a strong signal. This will not work with a weaker signal. And the reason why it will not work with a weaker signal is because even though at each action potential peak calcium is entering, the removal of calcium is always active, so it's removed. So the concentrations don't become very high at lower frequency of action potentials. But if we have something like this, and again, we're going to have our x-axis be time and potential millivolts, we have high frequency of action potentials. What will happen is you'll start to see them space out a little bit more as time goes by, more as time goes by, and eventually it'll be even more as we go down. So this space between them keeps increasing. Remember, this space is time, right? So the frequency of the action potential starts to decrease. Why? Because at every peak, calcium is entering and activating those calcium-activating potassium channels, making the membrane more permeable to potassium, thus making it more difficult to initiate the depolarization phase of an action potential. Okay, so let's draw this out, or draw the pathway. And this is what's happening at the AIS. Let's not make the mistake of thinking this is happening anywhere else. This is happening at the axon initial segment and only at the axon initial segment. So we have the PSP coming in from the soma and the dendrites, right? And that leads to the activation of voltage-gated sodium channels, which then leads to depolarization, which then leads to an action potential forming. And of course, you have the positive feedback from depolarization, which leads to more voltage-gated sodium channels opening. But every time an action potential is formed, you have the activation, or the opening, of voltage-gated calcium channels. This leads to the activation of calcium activating potassium channels. And what will they do? They will inhibit depolarization. It's a little bit harder to draw this out for the other channel, the rapidly activating potassium channel. So I could draw it out, but it's not really as clean as this one, I guess. But let's attempt it. We have a PSP, voltage-gated sodium channels are activated. You have depolarization, action potential. And of course, you have the positive feedback loop here. But if the PSP is low, so low PSP, you have activation of rapidly activating potassium channels. And this really is dependent on how low the PSP is. The lower, the more this is going to be activated. And this will inhibit depolarization. So at higher PSPs, this goes away. This whole thing right here goes away. But at PSPs that are kind of lowish, what you'll have is a grading of this, meaning that the membrane is much more permeable to potassium when the PSP is low, but it starts to lose that permeability to potassium as the PSP is higher. And maybe we can draw that out too. So if I was looking at it in this way, permeability to potassium and PSP as my x-axis, and we're going to say that threshold here, because really before threshold to initiate an action potential, it's not really important. So we'll just go up here. And what we'll have is we'll have maximum permeability to potassium, and it starts to get lower as the PSP increases. And that just means that the frequency of action potentials will increase as the PSP increases. So all the computations that are being made at the AIS, it's simply making the membrane more permeable to potassium. Because if you make it more permeable to potassium, it takes longer to initiate an action potential, and that just lowers the frequency. And the adaptation is just an adaptation. I mean, you don't want your nerves to be firing at full maximum, even though they're receiving strong signals. They adapt to the signals in different ways. And this is one form of adaptation. This is not the only form of adaptation. Let's just be super clear about that right now. This is just one form of adaptation. There's other forms of adaptations that occur at a neuron all the time. So we'll leave it at here because this is the end of 2.2, and we'll continue with 2.3 in the next video. Thank you, guys.